Okay, so today we're going to continue our study of the Riemannian isometry group of the upper half plane and the group of Riemannian isometries that preserve the orientation. We're going to indicate the prototypical geometric behavior of the orientation preserving isometries. And then we are going to finally visit the Poincare disk and transport our study for the upper half plane to the Poincare disk. So let me start by recalling that in the last lecture we obtained an explicit formula for arbitrary Riemannian isometries of the upper half plane. Namely, we saw that an arbitrary Riemannian isometry is either an element of PSL2R, right? So that it's given as a Mobius transformation associated to a real 2x2 matrix of determinant 1, right? And with the correspondence rule given by Mobius' famous formula, or it is given by some sort of modified Mobius formula for a matrix of determinant -1. And then in particular, from these explicit descriptions, one can immediately obtain that actually PSL2R is already the whole group of Riemannian isometries that preserve the orientation. And indeed, right, because any Riemannian isometry not here, not here, not in PSL2R, has determinant is given by a matrix of determinant -1 that you see when you compute the derivative of this as a differentiable function, gives you a negative, the derivative has negative determinant, and so it cannot be here. Right. So observe that this is not holomorphic, right? This is infinitely differentiable, but not holomorphic. Yeah, and then an exercise that somehow asks you to relate the notion of Riemannian isometry to the notion of simply metric isometry, right? So just an isometry, but only at the level of metric spaces. Of course, every Riemannian isometry of U is metric isometry, and somehow this exercise asks you to think about the converse, the possible converse. Okay, and now we go on to describing the full group of isometries of the upper half plane in terms of this subgroup and the group with the two elements, 1 -1. So define S star L2R to be those 2x2 real matrices of determinant 1 or -1. Of course, SL2R sits in S star L2R as a subgroup of index 2. And see, this theorem tells us that we have a function from S star L2R to the full group of Riemannian isometries, and that this function is actually surjective, right? That we have a function, well, of course, for any matrix of determinant plus or -1, we can consider the corresponding function in the case of determinant 1 or in the case of determinant -1. And that's a Riemannian isometry, and this theorem tells us that it's surjective. Exercise, this function is actually a group homomorphism, and its kernel is just plus or minus the identity. So here, yeah. So as you can see, then this becomes a group homomorphism that extends the group homomorphism going from just SL to R. Here, just given by a Mobius formula, right, that to any matrix associates the corresponding Mobius transformation. Here I should write also R. Okay, and now the next result is that S star L to R is a non-trivial semi-direct product of SL to R and this group plus and minus 1. And the proof, if you are already well acquainted with semi-direct products and their correspondence to split short exact sequences of groups, you can see that in order to prove this, it suffices to show that that this short exact sequence splits on the right, where, of course, here you see here I have the determinant, which of course goes then to plus minus 1, and of course the kernel of the determinant is precisely SL to R, and the splitting is to produce the splitting, that is a group homomorphism with the property that this composition is the identity here. For that, I only need to produce a matrix here different from the identity matrix, but also whose square is equal to 1. Right? So because I want S to be a group homomorphism, and that splitting is one such splitting is just given by sending minus 1 to this matrix. In terms of a group action on this group on this group by automorphisms, it is given as follows: the group automorphism of SL2R corresponding to the element minus 1 here acts on a 2x2 matrix in SL2R by simply conjugating by this matrix, right? So the action on such a matrix is simply negate the off diagonal entries, right? So so recall that somehow roughly speaking, the relation between the splitting and this group action of this group on this one by automorphisms is that the action on this group corresponding to an element of this group has to correspond to conjugation by the image under the splitting, right? So that's why it's this one, right? And that correspondence is somehow a standard result on semi-direct products. So this presents, this theorem then presents S star L to R as this semi-direct product. Now, the group of orientation preserving isometries of the upper half plane is PSL to R. So that is, from SL to R, I have to mod out plus minus the identity. So what I'm really interested in, at least in regards to the upper half plane, is not this group is not S star L2R and in terms of SL2R, but rather the quotient of this one by plus minus the identity in terms of this one quotient by the plus minus the identity. Although this result is already nice on its own right, but that's not my focus in terms of the upper half plane. So PS star L2R is the corresponding quotient. Yeah. And then since this is a group homomorphism with somehow the correct kernel, it induces a group isomorphism, PS star L2R and the codomain, right? So the full group of isometries. So somehow this gives me a concrete. This already gives me a concrete description of this Riemannian isometry group, because I can see that it is almost the group of 2 by 2 real matrices with determinant plus minus 1. I only have to identify a matrix with minus itself. So this is almost a group of matrices somehow. Now I want to describe this one, that is this one, in terms of PSL2R, in a way similar to this theorem. And that's the next theorem, that PS star L2R is a non-trivial semi-direct product given by some action of the group of two elements on PSL2R by group automorphisms. Or equivalently, that there is a split, a short exact sequence that splits on the right. So we have our short exact sequence from above, right? So this one is this short exact sequence, and what I see is that in both I'm modding out by the same subgroup, and so I obtain here an injective group homomorphism, and of course the determinant factors through the quotient, because the determinant of minus the identity is 1. So I have this induced short exact sequence with the property that these two squares commute. Yeah, and notice that here I have actually the identity. Somehow what happened is that here there was a collapse, here there was a collapse, but not here. Here everything was completely preserved. And that really helps me, because here I know I have a splitting. This is the S from here. And now, and I know that this composition is the identity, or if you want, this composition is the identity. Yeah. But you see, this is equal to this. So really, this S, well, this S composed with this projection gives me a splitting of the lower short exact sequence. And the theorem follows, again, by the correspondence between splittings of short exact sequences and semi-direct products. Okay, so this gives really a full description of the Riemannian isometry group, pretty much in terms of PSL2R, and a simple conjugation. See, a very simple action. Okay, so this is something to stress is that in the three models that we have encountered so far of the hyperbolic plane, namely the hyperboloid, then the Poincaré disk, and the upper half plane. This is the first time that we are able to fully compute a Riemannian isometry group. And this full computation then somehow allows us to complete the computation we started in the hyperboloid, and it also will allow us to give a full description of the full Riemannian isometry group of the Poincare disk. Which, by the way, the Poincare disk we still have to give some to study it in more detail than we have. So this is the corollary of all the isomorphisms that we have collected. Yeah, and then let us give a brief description of the geometric behavior of the orientation preserving Riemannian isometries of U, which is the same as saying to give a description of the geometric behavior on U of the Mobius transformations that preserve U bijectively. So if you remember, when we were speaking about Mobius transformations in general, we gave some description of their geometric behavior, and this description was achieved by first studying the so-called standard examples, and then somehow pushing that description of that geometric behavior through conjugation, right? Through conjugation by arbitrary Mobius transformations, using the fact that arbitrary Mobius transformations send circles to circles and are conformal, that is, preserve angles, right? So somehow we are simply going to specialize the description we gave back then to the case of Mobius transformations that preserve U bijectively. And so this is in the parabolic case. Well, in the parabolic case, when I consider nu as a Mobius transformation of C bar, and here it should be C bar. Well, it has exactly one fixed point by definition of what it means to be parabolic. Let's say Z0. And now this Z0 has the property of attracting all the iterations of nu at arbitrary points of C bar, as we saw, and which can be already seen in the case of translations, right? I mean, we saw that every parabolic transformation of C bar is conjugate in mob C bar to a translation, and if you think about it, translations obviously have the property of that the infinity is an attractor for arbitrary positive iterations of the translation at arbitrary points of C bar. So we definitely have this. But so you see, in particular, for the points in U, one has this, right? So Z0 has to be in U bar, because otherwise there would be some point in U for which some iteration leaves U, right? Kind of falls outside U, in contradiction to the fact that nu preserves U bijectively. Yeah? So Z0 has to be then in U bar, but then applying the same argument, but now to things in minus U, so to things in the lower half plane, we see that Z0 cannot be in U, because otherwise there would be things outside U bar, so things here, that would eventually come into U, again contradicting the fact that nu is bijective and preserves U bijectively. So Z0 has to live in R bar. Okay, it has to live in R bar, and then the corresponding picture is this one, right? And by that, what I mean is that the pink circles, which are the circles in C bar contained in U bar and tangent to R bar in Z0, those circles, the pink ones, each of them is stable on their all integral powers of nu. And notice that depending on nu, the iterations along one such circle, and thus any such circle, can move either in the counterclockwise sense, in which case it's kind of the same in all of them, or in the clockwise sense. Okay, and now the orthogonal family, that we defined for this family of circles, you see, it precisely contains these shortest curves in U. Right? So somehow the behavior is, for instance, if the iterations move in the counterclockwise sense, somehow is something like this whole shortest curve is mapped by nu to another such shortest curve, let's say like this. Yeah, and then the second iteration would move it to another such, like this, etc. Right? Let's say another one, although yeah, my drawing is far from perfect, and so on. Right, and then somehow things eventually start to come back after a while. That picture was not very far from perfect. So that's the parabolic case. Of course, if Z0 is infinity, then the pink circles simply look like horizontal Euclidean lines, and the purple ones look like vertical lines, right? And nu, then you can see is a horizontal translation, and somehow moving in the counterclockwise or clockwise orientation corresponds to either to the translation being either to the left or to the right. And then I leave you as an exercise to think counterclockwise corresponds to translation to the left or to the right, and clockwise, the clockwise sense would correspond then to translation to the left or to the right. So that I leave you as an exercise to think. Now the next case, the hyperbolic case. Well, of course, if you give me a Mobius transformation of C bar that preserves U bijectively and is a hyperbolic Mobius transformation, here again it has to be C bar. Well, it has two fixed points in C bar. Now, one of the 2 points is attractor and the other one is repulsor. And from this, and for this, think again in terms of the standard examples. I mean, to think about the standard examples, one somehow forgets a little bit about the upper half plane and thinks only about the standard examples, and then there one sees that 0 is either 0 is attractor and infinity repulsor, or 0 is repulsor and infinity attractor, and this depends on the norm of the or absolute value of the multiplier. Okay, and then mapping back to now our situation, one of them has to be attractor and the other one is repulsor. Say that Z0 is attractor and Z1 is repulsor, up to exchanging them, right? Kind of up to changing the ordering, let's say Z0 and Z1. Okay, and then an analysis similar to the analysis that from here, that from this allowed us to deduce that Z0 was in R bar. A very similar analysis allows us to deduce that both of them here in this case are in R bar. Okay, so both of them are in R bar. And now I have these segments of common circles to Z0 and Z1. And note that among all of the most of these segments of common circles are not shortest curves. Actually, only one of them, and it's the one that happens to be orthogonal to R bar. So okay, so they are not, but still the iterations of nu can happen along each of them. Right? In other words, each of these segments is stable under the action of all the integral powers of nu. And of course, the dynamics moves away from the repulsor and towards the attractor. So for instance, if this were the case, that this is Z0 and this is Z1, that is, if this one is the attractor and this one is the repulsor, then the iterations start at some point, given any point in any such orange segment, the iterations start moving away, and they never reach. Right? It's kind of these limits. They are limits, but one never, if one takes a point different from Z0 and Z1, one converges, but one never stabilizes. In other words, the sequence is not stationary. And if this was Z1 and this one was Z0, it would be the other way around. Oops, sorry, Z0. So in this case, things move away from Z1 and towards Z0. Okay, now the family orthogonal to the orange circles, right, to the orange segments, which is to the orthogonal to these segments of common circles. Well, notice that R bar is one such common circle. So the orthogonal family consists in particular of these segments that are orthogonal here. So that is, they are shortest curves in the upper half plane, and one such is always sent to another such. Etc. Okay, so this is how the geometry is organized in the hyperbolic case. And finally, in the elliptic case, suppose that now I have my elliptic Mobius transformation that preserves U bijectively. it has two fixed points in R bar, let's say Z0 and Z1. And somehow we already know that around these 2 points, somehow it behaves as if it were a rotation. Okay, but now let's see these fixed points where they are located, just as we figured out where the fixed points were located in the previous cases. So for that, take a matrix in SL2R representing the Mobius transformation. Now, since these two fixed points are not infinity, yeah. So the reason why they are not infinity, actually none of them actually belongs to R bar, and the reason is that let's say that one of them belongs to R bar, right? And then I look at the image of R bar under nu. So unless in this case nu were behaved like this 180-degree rotation on R bar, unless that happened, the image of R bar would have to be some other circle through the fixed point. But then nu would not preserve U bijectively, right? Because these points very close, these points very close, which are outside U, would go inside, let's say, strictly inside U. Okay, so that leaves, so if one of the fixed points is in R bar, nu has to be this 180-degree rotation here. But then you see things if this is the fixed point, things very close here are mapped to things very close here outside U. And so again, nu doesn't preserve U bijectively. So it cannot be the case that that nu has a fixed point in R bar. All right, and so in particular, neither of them is infinity. And here, when I consider this matrix, since none of them is infinity, what I can see is that gamma is not zero. Right? Because if gamma were zero, then infinity would be a fixed point. Okay, so gamma is not zero, and the fact that these are complex numbers that are fixed points amounts to them being roots of this polynomial of degree 2, because gamma is not zero, with coefficients in R. Recall that all these 4 entries are in R. But the roots of any such polynomial are conjugate, are either one real number with multiplicity 2, or 2 conjugate complex numbers, different complex numbers. The first case is not possible because that would mean that these 2 are the same and are real. So they are the same and belong to R bar. So that's not the case. So they have to be conjugate complex numbers. Okay, and this means that exactly one of them lies inside U, and the other one is it's a complex conjugate. And then I see these are the Apollonius circles of this and its conjugate contained in U. And now exercise such Apollonius circles, the ones contained in U, right? The Apollonius circles of the 2 fixed points, but the ones contained in U, those Apollonius circles are precisely the hyperbolic circles with center the fixed point of nu belonging to U. And as you recall, since nu is elliptic, each such Apollonius circle is stable under all integral powers of nu, and actually nu behaves as some sort of rotation along such circles. And now such rotation may or may not have a finite or infinite order. Right? This or in the clockwise sense. Okay, and when I take the orthogonal family, you see the point is that R bar is one Apollonius circle of this one and its conjugate, because it's actually the Euclidean mediatrix. And so the family orthogonal to the Apollonius circles consists of gives shortest curves in U, because they have to be orthogonal to R bar. And nu permutes them, right? So it's something like one such is mapped to another such, and is mapped one such is mapped to another such, is mapped to another such, is mapped. Okay, and now that my drawings start becoming really ugly, but is mapped to another such, is mapped to another such, etc. Yeah, and you see these stable curves. I mean, these curves that are stable under all integral powers of nu are precisely the circles, the hyperbolic circles with this center. So this intuition that the elliptic transformations are rotations is correct somehow, because somehow all these ones simply get rotated, and that somehow that coincides with with them being each stable under all positive powers of nu. Okay, so let's talk about the Poincaré disk, and somehow it's going to be a little unfair, because you see the Poincaré disk turned out to be to play an essential role in our computation of shortest curves in the hyperboloid, because we used it to compute to be able to compute certain integrals, and it also played an essential role in our full description of the group of Riemannian isometries of the upper half plane, because there was certain type of transformation that looked like a rotation, and now we know it really looks like a rotation in the upper half plane, that was simply easier, whose existence was simply easier to see or to be convinced of in the Poincaré disk, because in the Poincaré disk there is one special point, which is the center, the Euclidean center of the Poincaré disk, and we don't have such a point in the upper half plane. And so even though the Poincaré disk already played essential roles, since we already proved many things for the upper half plane and the hyperboloid, now we are going to skim very quickly through the Poincare disk, and then this is a bit unfair because then that may convey the idea that that is less important, but actually, you see, it already played a very important role. Okay, having said all that, recall that the Poincare disk is defined as a Riemannian manifold to be the unit disk in the complex plane with the Riemannian metric obtained by pooling Minkowski's Riemannian metric on the hyperboloid to the disk via the stereographic projection. Recall also that there was this theorem that whose proof was left as an exercise that computes explicitly this Riemannian metric for the Poincare disk, that gives an explicit formula. And recall also that there is some intuition to be drawn from this formula, which is that close to the complex unit circle, distances become really large. So short Euclidean distances become hyperbolically very large. Recall also that we have an explicit biholomorphism between both of them, and this biholomorphism is actually given by a Mobius transformation, the so-called Cayley transformation, and that actually this is the one that we used to pull this the Riemannian metric that we just mentioned for D to U. Okay, now the theorem is that you see, just as we proved that every Mobius transformation of C bar that preserves U bijectively is an orientation preserving Riemannian isometry of U, that's the corresponding statement is true for the Poincare disk. And conversely. And this means that the group of Riemannian isometries of the Poincare disk that preserve the orientation is this quotient of SU11 modulo plus minus the identity. Why does SU11 appear? Well, because here we are, well, in both, we are speaking about Mobius transformations that preserve the disk bijectively, and if you recall, we proved that those are precisely those of the form Mobius transformation of a matrix in SU11. And also recall that SU11, the elements of SU11 are precisely those of the form alpha, beta, beta conjugate, alpha conjugate of determinant 1. So the proof, we're going to go just very quickly over the proof, essentially because we already did the proof in detail for the upper half plane. That's essentially the reason. And that the Cayley transformation is a Riemannian isometry, pretty much by how the Riemannian metric on U was defined, was pretty much defined precisely making the Cayley transformation a Riemannian isometry. Now, being nu one such, what happens? Well, that conjugating with the inverse of phi, right? So that kind of going first to the upper half plane, and then going first from the upper half plane to D, and then here applying nu, and then going back. This since nu preserves this bijectively, this composition preserves U bijectively, and so it's an orientation preserving Riemannian isometry of U, and this one is also an orientation preserving Riemannian isometry, and so it's inverse. So nu is an orientation preserving Riemannian isometry of the Poincare disk. Conversely, so if you give me any Riemannian isometry, and here I should have said orientation preserving, well, then this one is a Riemannian isometry of the upper half plane, yeah, and actually here I have to say I should have said orientation preserving, and so this one is also an orientation preserving, this one, yeah. So it can be presented as such composition as mu of some matrix in SL2R. Okay, and then once one has that, one somehow just composes with phi on the left and with the phi inverse on the right. But composing with phi on the left is pretty much you just have to multiply with this matrix. Okay, and 3. Well, 3 it's just immediate from the fact that SU11 is conjugate to PSL2R precisely using this very same this matrix, right? So the isomorphism iso-re of U GU isomorphic to SL2R modulo plus minus the identity matrix. This isomorphism can be just transported to one such isomorphism, right, with this phi. So I will leave you as an exercise to do that explicitly, but now it should be clear. And then explicit formulae for all Riemannian isometries of the Poincare disk. So any such Riemannian isometry is either the Mobius transformation associated to some element in SU11, or it's a modification of Mobius formula for some matrix in SU11. And you see here there is no minus sign accompanying this W conjugate, but you see the point is that if I draw the Poincare disk, conjugation is reflection through this horizontal Euclidean line, and that horizontal Euclidean line corresponds precisely to the positive part of the imaginary axis, and you see reflection, and so reflection here corresponds to reflection here, and reflection here. This one is really given as W goes to minus W conjugate. But so that is why here there is a minus sign, but here there is none. The proof, I leave it as an exercise. You pretty much by now should know how to prove it. You have to conjugate with the Cayley transformation or its inverse. Yeah, and then at least the basic idea should be clear, and I leave you to work out the details. And then, since the Cayley transformation is a Riemannian isometry, the shortest curves and the hyperbolic circles here precisely are precisely the images of the corresponding ones here. And I know that the Cayley transformation is also conformal and sends circles to circles. So Euclidean circles to circles in C bar to circles in C bar. So the shortest curves in D are precisely the segments of circles, the segments contained in D of circles in C bar perpendicular to the unit circle, which I like to think of as the circle at infinity of the hyperbolic plane, okay? Because the complex unit circle is not contained in the hyperbolic plane. Okay, and now note note that in particular the Euclidean straight line segments through the complex origin are some of such segments. So these ones are shortest curves, as long as they pass through the origin. Okay, and then such segments. Okay, and then how about hyperbolic circles? Well, we know that the hyperbolic circles in the upper half plane are precisely the Euclidean circles contained in U. So just map those to D, and what you obtain is that the hyperbolic circles in D are precisely the circles in C bar entirely contained in D. So they are the Euclidean circles entirely contained in D. Right? In D. So that means that if I take one point here and then I take a tangent, an Euclidean tangent circle here, that one is not a hyperbolic circle because it's not entirely contained in D. Namely, the tangency point is not in D. So so it's like, don't get deceived. These ones actually receive the name of horocycles. Okay, and then that was it about the Poincare disk. Okay, sorry. I still have to close with the geometric behavior of the orientation preserving Riemannian isometry. So that was almost it. Okay, but by now it's just take whatever we know about the upper half plane and map it to the Poincare disk. So in the parabolic case, the fixed point, well, in the case of the upper half plane, the fixed point lied in R bar. So now the fixed point lies in the unit circle. And then the parabolic transformation looks like some sort of degenerate rotation. And I say degenerate because the rotation seems to be around this point, which is also a limit point, right? So, and then of course either counterclockwise, as I just drew, or clockwise. And then let's say in the first instance, in the counterclockwise sense, one such curve is mapped, one such shortest curve is mapped to another such, mapped to another such, mapped to another such, mapped to another such, etc. Right? Or it could be clockwise. Okay, so you see here, it seems as if counterclockwise corresponds to horizontal translation. But anyway, hyperbolic case, the two fixed points now have to lie in the unit circle, because in the case of the upper half plane, they lied on R bar, and then the stable stable segments, of which only one is a shortest curve. Such shortest curve is, by the way, called the axis of the hyperbolic isometry. And then in the orthogonal family, one such curve, which is a shortest curve, is mapped to another one, 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 etc. Okay, so the picture is not so nice. And that this what I just drew is, if this is a repulsor and the other one is an attractor, and then there's the corresponding picture if it's the other way around. And finally, in the elliptic case, one fixed point has to lie inside D, the other one has to be completely outside, and actually completely outside the bar. And then the fact that in the upper half plane, the two fixed points were related by one being complex conjugate of the other corresponds now to the two fixed points being related by this kind of inversion. So this I leave as an exercise. It's an easy exercise. Kind of the crucial observation is that in the case of the upper half plane, R bar is in the case of the upper half plane, if I have R bar and I have two conjugate complex numbers, it turns out that R bar is the mediatrix of the two, as we said before, and being the mediatrix of the two is exactly being the Apollonius circle for the value R equal to 1. And that being R, the value being R equal to 1 maps to, you see now I have my 2 points here, and the image of R bar has to be the Apollonius circle for the same value R equal to 1, according to the computations we did when we showed that the image of an Apollonius circle with respect to a Mobius transformation under a Mobius transformation is again an Apollonius circle. And so this one has to be an Apollonius circle, the Apollonius circle for the value R equal to 1. And that can be translated onto the condition that these 2 points are related by this transformation. So I'd leave the details as an exercise, actually as a hand-in exercise. And that finishes also our treatment of the Poincare disk. And then as you can see, it may seem that it's the least relevant. It may seem, yeah, but it is not. It really played a crucial role a couple of times. Now, let me show you kind of some animation of Riemannian isometries, orientation preserving Riemannian isometries of the Poincare disk. You can find this, the link, I put it in the notes. I didn't do it. It was Chris Jerdonek. And here you can see this would be the behavior of a hyperbolic one. Here you can see this is the repulsor, this is the attractor. This would be the behavior of an elliptic one. Here, that is the fixed point contained in the disk. And you can see that it really looks like a rotation around that point. And this is the case of a parabolic one with this fixed point. And then here you can see that it doesn't matter what point we take in D, or even in D bar, or for that matter in C bar. In the limit, you tend again to the point. Although, of course, here the animation stops after finitely many steps. Yeah, so I really recommend you to have a read of this entry. I think it's very useful. And it also includes some words about orientation reversing isometries. And that was it for today. If you are still not well acquainted with semi-direct products, you can have a look at these notes and video. Here is the link to the website that I just showed you, and the handy exercise. And that was it for